we are going to do our first sample random oracle model proof. To do that, we will need to work with the RSA assumption and an encryption scheme based on that. Now, we first define a generation algorithm for this RSA assumption. It takes the security parameter as the input, and what it does is the following. It picks two prime numbers, P and Q, randomly, such that, let's say, they are primes of length, let's say n, okay? Then it computes a value n that's equal to P times Q. This value n defines the composite order group Zn star. Remember, integers modulo n that are relatively prime to n. And the group operation is multiplication modulo n. This group, remember, has order phi of n that is p minus 1 times q minus 1. There are that many elements in this group. Then this gen algorithm computes two values, e and d, such that e times d is equivalent to 1 modulo this order of the group, p minus 1 times q minus 1. So eventually this gen algorithm outputs n, e, and d. The RSA assumption states the following. So this is an assumption. The RSA assumption says, for all probabilistic polynomial time adversaries A, there exists a negligible function, let's say neg n, in the security parameter, such that if we consider this following experiment, we run the gen algorithm using this security parameter, it outputs n, which defines the Zn star group, e and d, and we pick, let's say, a random value x from Zn star. And then what we do is we give the adversary, of course, the security parameter n and e, but not d. We don't give the adversary d. Instead, we give the adversary x to the power e. So we compute this, we give it to the adversary, and we expect the adversary to return back x, essentially the eth root of the element in the group that we gave to the adversary. And the RSA assumption states that for all probabilistic polynomial time adversaries, this probability is negligible. Now, using this assumption, we are going to create an, let's say, RSA-based encryption scheme. Okay, let's call this scheme pi. The scheme pi will have this key generation algorithm, where n and e constitute the public encryption key, and d is our secret decryption key. The encryption in this RSA-based scheme that we are developing will use this public key and will take a message. And we are going to assume that our message has length, let's say, some L of n, where L is some polynomial in n. So we have a fixed length message space. It needs to output some ciphertext. What it does is the following. It's going to pick a value r from Zn star, and it's going to compute r to the power e modulo n. This will be C1. Then it's going to send r to the random oracle. it will output some y that is of the same length as the message. So our random oracle on input a group element R outputs some random output essentially of the same length as the message. So we compute C2 similar to one-time pad as y XOR our message M. And this C, the final ciphertext we output, has two parts, C1 and C2. What would be the corresponding decryption? Remember, decryption uses the secret key in an asymmetric scheme, and it takes the ciphertext as the message. Its goal is to output the message back. Ciphertext as the input. What it's going to do is as follows. Remember, this ciphertext has two parts, C1 and C2. It will take C1, compute C1 to the power D modulo n. Now remember, C1 is R to the E mod n. We are computing R to the E to the D mod n. This is essentially R to the ED mod n. ED is equivalent to 1 modulo the order of the group. Therefore, this thing will give us back R. Now, once we have R, we will send R to the random oracle. The random oracle, since we are giving back the same R, it will return us back the same Y. Now that we have Y, our job is extremely easy. We compute C2 XOR Y. This will give us back the same message M. So this is a correct encryption scheme.